Hello everybody, today we begin our last final topic, which will be integrals of polar equations. So this whole thing will come in two videos. So we will talk about polar areas, then we will talk about polar lengths. Now, this is going to be a little bit trickier than just finding areas underneath polar curves. Obviously, that was a fairly easy affair. Now we need to determine how to find areas under polar curves. So we will look at that now. Okay, so we got to start with a couple of definitions. I really want to derive this. So if I have a circle, so the circle is the most common polar equation. If I have the circle, a bad circle, but it is a circle, we're calling it one. And I want to find the area of some sector, right? So I have an angle theta. Well, we remember that from pre-calculus, if I want to find this area of this sector, then I get 1/2 r squared theta for my area. So now we want to generalize this. So now we have sectors. We know sectors. So let's say I have an angle theta. Then I have a polar curve. That's my polar curve. Well, now, because theta is our independent variable, theta is going to be the value that we integrate over. So we integrate over tons of little d thetas. And these d thetas will correspond to r values here. And we want to find all of these little areas. We want to find all of these little areas in here. These are each going to have r values, and they're each going to have theta values over little d thetas. So, well, what does this mean? So this means that we can generalize this sector definition and make it into an integral. So we want to find the area, and the area is going to be the sum. Then we're generalizing this, so we've got 1/2 r squared, but now this is going to be a function of theta because r changes with respect to theta, with respect to a little delta theta that we have. I could index this, but I can't be bothered. And so what we do is we can transform this into an integral by taking the limit. So we get the integral between a and b, some starting angle and some ending angle, 1/2 r squared of theta d theta. Now this equation isn't super tricky. It's just applying it that we need to work on. Obviously, it's going to involve a lot of trick, but I think that will be fine for us. Let's try a couple of examples. So I want us to find the area bounded by one loop of r of theta equals cosine of 2 theta. Okay, so it's going to be helpful to draw this out. So if we remember what this looks like, this is going to be a rose. We have the 2 theta, so this means that we have an even number of thetas, or an even number in the argument. So that means that we're going to have 4 loops. And because it's cosine, these loops are going to be either parallel or perpendicular to our axis. Now, it doesn't really matter how well I draw this. It just matters that we get the angles down. So we're going to have one loop here. So we get one loop. We get another loop. We get another loop. Obviously, these loops are all the same size. Obviously, this has a lot of symmetric properties that we can use to make our integrals easier as well, which is nice. So we want to find this here. Now, given that this is all symmetric, we know that these are each going to be swept out by angles of 90 degrees, but they're going to be skewed. So you've got here theta equals pi over 4. Theta here equals negative pi over 4. Okay, so now we know where we're going to be integrating. So our theta is going to be swept out by negative pi over 4 to pi over 4. All right, so we get r squared of theta. We need to find r squared of theta. That's just cosine squared of 2 theta. We just square this. Now we're going to plug it into an integral. So we get the area is equal to 1/2 of the integral between negative pi over 4 and pi over 4, cosine squared of 2 theta d theta. Now we can use symmetry here to say that this is actually just the 2 times the integral between 0 and pi over 4 of cosine squared of 2 theta d theta. Obviously, this is a symmetric function. And now we just need to solve this. We know the cosine squared formula to turn that into a cosine of 2 theta kind of thing. So we get the integral of 1/2 the integral 0 to the power of 4 of 1 plus cosine 4 theta d theta. Okay, now these integrals we can do because this is just a numerical argument in there, and we just take out the constant, divide. So we get 1/2 times theta plus 1/4 sine 4 theta, integral, or not integral, and we're evaluating between 0 and power of 4. Work that out with the fundamental theorem of calculus, and you'll get pi over 8. Right, so we get pi over 8. So that's the area of this guy in here. All right, let's move on to a more nuanced problem. I want us to find the area between r equals 3 sine theta and r equals 1 plus sine theta. Okay, now this is going to be a little bit more funky because we're dealing with areas between curves. So if we draw this out, we obviously know what r equals 3 sine theta looks like. This is some sort of circle along the y, or along our y-axis here, or I guess we're dealing with polar, we shouldn't really say y-axis. And then we've got another guy in here, r equals 1 plus sine theta, and that's going to look something like this. A little heart-shaped thing. And we want to find these intersection points because that's what we're going to integrate between to get our area. All right, so let's try it. So to find where these intersect, we just set them equal to each other. We get a trigonometric equation. Subtract sine theta from both sides. Get 2 sine theta equals 1. Divide by 2, sine theta equals 1/2. Now this is easy. We know when sine theta equals 1/2, and we're going between 0 and 2 pi because we don't want to keep integrating around and around. We get theta equals pi over 6 and 5 pi over 6. So now we have an integral between pi over 6 and 5 pi over 6. We square both of these functions, and we subtract this one from this one, or we subtract this one from this one. You get area equals 1/2 integral between pi over 6 and 5 pi over 6, 9 sine squared theta, minus 1 plus sine theta squared d theta. All right, so now all that's left to do is we're going to do all the algebra we need to inside of the integral, and we get integral between pi over 6 and pi over 2. Using symmetry, we can take this and this as being equal to this and this. We can take this equal to that. We just do 2 times this. So then, this looks like a kind of little creature, like a little alien, never mind. We get the integral between pi over 6 and pi over 2 of 8 sine squared theta, minus 1 minus 2 sine theta d theta. We can simplify and use our trigonometric rules so that we don't have a sine squared. So we get integral between pi over 6 and pi over 2, 3 minus 4 cosine 2 theta, minus 2 sine theta d theta. And from here, all that's left to do is evaluate this fairly trivial integral. We get 3 theta minus 2 sine 2 theta plus 2 cos theta, evaluated between pi over 6 and pi over 2, which is equal to pi. All right, so we found the area that's in here. So now we have discussed polar areas fairly nuancedly, and obviously you can do all the sort of stuff you want with these integrals, similar to parametric equations. In the next video, we are going to finish off our final video of single variable calculus by talking about polar lengths, so arc lengths and all that sort of good stuff. All right, we'll see you in the next one. Bye.